Alright, so here we're going to start section 2.5, and we're going to focus on the fundamental theorem of algebra. So we want to understand the fundamental theorem of algebra, and also we're going to look at how to find possible rational roots. So what is the fundamental theorem of algebra? Well, the fundamental theorem of algebra says if f of x is an nth degree polynomial where n is greater than 0, then f has at least one 0 in the complex number system. So the important thing to understand about this is telling us about the existence of at least one 0. Now another thing to pay attention to is it's saying that it has at least one 0 in the complex number system. That doesn't mean that it has to have an I value. Remember, all real numbers are part of the complex number system. So it's not saying that we have to have a 0 that has an I in it as part of our solution. It's just saying that the complex number system is the largest number system we're dealing with right now, so therefore we know that it has to be in that system. This then leads us to the linear factorization theorem, which tells us if f of x is a polynomial of degree n, where n is greater than 0, then f has precisely n linear factors, such as f of x equals a sub n times the quantity x minus c sub 1 times the quantity x minus c sub 2, so on, times the quantity x minus c sub n, where each one of these binomials is a linear factor. And c sub 1, c sub 2, all the way up to c sub n are complex numbers. Again, don't get hung up on the complex number idea. Of what we're saying is that the complex number system is larger than the real number system and includes the real number system, so therefore they could just be real numbers also, but that means they're complex numbers as well. So this should be something, this is actually something we've already talked about, and so these two theorems together are just telling us that whatever the degree of the polynomial is, that's how many zeros we need. Whether those zeros are real numbers or complex numbers, which again, real are part of complex, that doesn't matter. That's not what this is telling us. This also is not telling us how to find those zeros or factors. It's just telling us that they exist. Okay, so now we're going to look at a test that, one of the tests that helps us find those actual factors or zeros, and that's called the rational zero test. And so what the rational zero test says is if we have a polynomial, so if polynomial f of x equals a sub n times x to the n plus a sub n minus 1 times x to the n minus 1 plus a sub 1 times x plus a sub 0, so our standard notation for a generic polynomial, has integer coefficients then every rational zero of f has the form P over Q. So what are P and Q? Well, first let's restrict them. So where P and Q have no common factors other than 1, and P is a factor of the constant term A sub 0, and Q is a factor of the leading coefficient. A sub n. So let's look at that again. So what is this saying? So a few key words we want to make sure to understand. That the polynomial has to have integer coefficients. So a sub n minus 1, and so on, a sub 1, a sub 0. All of those have to be integers. And we're talking about just rational zeros. So if there are irrational zeros in the polynomial, this test doesn't help. If there are complex zeros, and again, when I'm saying complex, I'm specifically referring to zeros that have an I in them, then this test does not help. So this is only going to help us find rational zeros. Now, remember, rational numbers can be whole numbers also. So they could be fractions or they could be whole numbers. And to find them, we find all of the factors of the constant term and all of the factors of the leading coefficient. And if there are rational zeros, they are going to be some combination of factors of the constant term divided by factors of the leading coefficient. So that's what this test is telling us. Okay, so let's look at an example using this. So we want to list all of the possible rational zeros. That's what the rational zero test does for us. Then we want to find all of the zeros, state the x-intercepts, write the function in completely factored form. So first, let's list the possible rational zeros. So we just learned from the rational zero test, this is the factors of the constant term divided by the factors of the leading coefficient. So what are the factors of the constant term? Well, the factors of 9 are 1, 3, and 9. Now we also need to keep in mind that factors of 9 are negative 1, negative 3, and negative 9 as well. So divided by, what are the factors of the leading coefficient? Well, the leading coefficient is 1, so the factors of 1 are 1 and negative 1. So now if we want to list these out, we would just write all of the combinations of these. So I'm going to write plus or minus 1, plus or minus 3, and plus or minus 9. You can see, though, that if the leading coefficient was something other than 1, and if the constant term here had more factors than 3, this could get to be quite a long list. Right now here, although I only wrote 3 numbers, remember it's plus or minus each one of them, so that's actually 6 possible rational zeros. Doesn't mean that any of them are actually going to be zeros, but these are the only possible rational zeros. That's the other thing we want to understand, is it's not saying that there could be other rational zeros also. These are the only possible rational zeros that could exist. Okay, so now I want you to finish this problem on your own and then come back when you're ready to check the answer. So now find actually all of the zeros, state the x-intercepts, and write the function in completely factored form. Pause the video, do that, and unpause when you're ready to check your answers. Okay, so we have our possible rationals. So now, in this case, I can factor this by grouping. So that's the easiest way to solve this. If I couldn't factor by grouping, one thing we could do is we could start to guess and check with these possible rational zeros using synthetic division or long division. Obviously you can see how that could be quite a process, and we might not want to do that, but that's how things were done before a calculator. Another thing we could do is we could use our calculator, put this in, and see if we get any zeros from our calculator that can help us. Again, in this case, the easiest thing to do is factor by grouping though, so I factor by grouping. I end up with x squared plus 9 and x plus 1 as my factors. Notice these, x plus 1 is a linear factor, but x squared plus 9 is not. So this is not completely factored yet. However, this is maybe not as intuitive on how to factor. So in this case, I'm just going to go ahead and continue to solve for the zeros. So I set this equal to 0. I end up with x equals plus or minus 3i and x equals negative 1. So the actual zeros are x equals negative 1, x equals 3i, and x equals negative 3i. Notice that the only rational zero was negative 1, which is one of our possible rational zeros. So that's good. If we ended up with a rational zero that was not one of our possibles, then we did something wrong. This is also our x-intercept then, so our x-intercept is the point negative 1, 0, and now the completely factored form, or product of linear factors, is going to be f of x equals x plus 3i times x minus 3i times x plus 1. So these are all linear factors. Alright, so we want to make sure we understand the fundamental theorem of algebra. It's something we've talked about a lot, or it's something that we do talk about a lot, but that we don't necessarily give credit to the fundamental theorem of algebra. But the idea that how many zeros are we looking for? We're looking for the degree of the polynomial. That's how many zeros we want, and some or all of those might be complex. Possible rational roots is the factors of the constant term divided by the factors of the leading coefficient.